Thank you, Keith. I'm Roger Rentala with HPE, and I'm here with Brent Gorder from ARM, and we're joined by our partners at Fujitsu. And we're here really to dive in a little bit on telling you a bit about our Apollo 80 system, which is really a joint effort. It comes out as an HPE Apollo 80 system, but it at its core is the Fujitsu A64FX processor, and with core ARM technology as an ARM-based processor. We also have ARM-based technology in there that we'll talk about. But first, kind of want to just a little bit of level set. This system is really purpose-built for high performance computing, and it's purpose-built and what very well suited for simulation applications. And we see these workloads throughout the energy industry. I mean, you guys have been doing this work forever, really since the early days of high performance computing. But typically that's been restricted into very specific domains, upstream domains for discovery and drilling plans and so forth. And then occasionally some downstream applications as well, and increasingly downstream applications as well for CFD, for production and process simulation, also environmental. But what we're seeing in your industry and hearing from you a lot is that there's new applications coming that are starting to harness the power of these capabilities that your organizations are already expert in, but maybe they're new applications and they're adjacent to this. But more than just adjacency, it's not all sitting within a high performance computing team and a team of experts on these applications that are entirely centralized all the time. Oftentimes, this data is dispersed, the locations of the compute resources dispersed, the locations of the human resources and the experts are dispersed into different organizations or different geographies. And so that means that it's really attractive to have a system that can be deployed in all of these different models. And I think that's something that Brent, you and I have talked a little bit about, just the idea that you can bring this deployably.
Yeah, and I think one of the other highlights to make, hopefully we'll make through here, is the difference in architecture. There's been a huge amount of effort put into GPU acceleration in some of these codes. And this particular architecture as a straight up CPU is an interesting alternative to that.
Yeah, I think you're right, Brent. I mean, there's no question that by coming at this and bringing the capability and the performance of accelerators and the step function performance, but bringing it in through the CPU, that makes it much more flexible, and it makes it much easier to take an existing application where core IP has already been developed and not ask an organization to then spend man years of effort to refactor that application. Rather, let's spend our energy and our effort a little bit to port and figure out what the best suited workloads and applications are that I control in my own organization, but also then to keep my software engineering investment focused on capturing the IP and building competitive advantage out of it. That time to value and code value effort rather than refactoring applications. So appreciate you bringing that up, right? We've seen over the years kind of this ongoing balance in supercomputing. Like when one thing gets fast and another thing is slowing the system down. In energy industries, you guys are really sensitive to this because a lot of the insight is derived after the simulations are run and you get into visualization. If you're going to look at a large scale reservoir simulation, the 3D modeling really helped. And early on, we really saw those bottlenecks because you want to interact with the data. But those bottlenecks are still in the systems, and we've been dealing with relatively fixed architectures for several years. And with that came some bottlenecks that we've even come to accept. The power consumption is high for high power processors. We increasingly try to get more power out of smaller and smaller real estate. We deal with limitations on Moore's law and so forth. That's been a challenge. But the core challenge that we've really been dealing with is that for simulation applications that are that are really demanding, we're moving a lot of data to the CPU, and no matter how fast that CPU is, if it's waiting for data, it's not that fast. And
remember the old definition of HPC was to turn a compute bound problem into an IO bound problem.
yeah,
The thing that the Apollo 80 brings to this is the massive memory bandwidth and the big vectors that allow you to process that data in place. So it's a very exciting architecture for that.
Right, and that memory bandwidth is going right to the CPU, and it's sitting right on the package with the CPU. So it's incredibly local, super low latency. And we'll get into that a little bit further. But the fundamental problem, the way this manifests itself in most of our systems that are deployed really broadly today, is that we build these systems, or we purchase these systems, or we sell them with very large memory. And that memory comes in big blocks that give you another pipe to the CPU. And that pipe is the only way to increase the bandwidth. So if I can do 2 blocks of memory, then I get twice the memory bandwidth. If I can do 4, I have 4 times the memory bandwidth. But what I'm really getting to increase the performance is that new pipe. My lived experience is I added more memory, I got more performance. But the reality is that what really provided that was just the bandwidth. It just happens to be packaged with all that memory. And so rebalancing that architecture is a goal of the Fugaku project, which is now the largest supercomputer in the world in Japan. And it's that very heritage that brings us the A64FX in the Apollo 80 in a much more deployable system. But because it's driving also to the CPU, and because we're also addressing vectorization with ARM scalable vector extensions, and really driving fast code, fast delivery to the CPU, and fast code through the CPU. And because it's CPU based, it's much easier to access it from a software development standpoint.
Right. So there's an interesting study that Shelf did at NERSC that talks about memory capacity versus bandwidth. And his argument is that we've been pumping up all these systems with big memory capacity for the side effect of the bandwidth. And the study shows that they don't actually use all of the capacity. So the Fujitsu A64FX here with the onboard HBM and no DIMMs allows you to explore that dimension of the architecture again.
Yeah, it does. And I think, in fact, we see similar studies from the NSF that in Stony Brook, the big scientific workloads. Their research says, not only are we underutilizing that memory, but in fact, 86% of the cycles and 85% of the workloads fit within like 32 gigabytes of memory with the operating system. We see it again in the UK on the Archer National Supercomputer. A lot of that memory is, just essentially unutilized or underutilized. And so this rebalancing provides an opportunity to shift that investment and gain some performance. So the system itself, this is a 2U server. This is not a big Fugaku size system. You can put 160,000 nodes into Fugaku, but you can put 8 into a 2U server right here on the HPE Apollo 80 server. That's 8 blades, or the 8 CPUs and 4 blades, and a standard 2U server. This is air cooled. It's very dense packaging, but the heat management is taken care of. So you can rack these and stack them. How much bandwidth are we talking about? We're talking about a terabyte a second of memory bandwidth. So classically in a x86 based system might be 256. Now we're starting to see 512 bytes of memory per second, megabytes per second. But that's still a long way from a terabyte a second. And again, to Brent's point, you're buying a bunch of memory to support that bandwidth. And because this is a purpose-built HPC CPU, we're getting full true 64-bit performance, which is really important for you guys. Over 3.1 teraflops of performance to the CPU when it's optimized. The HBM directly attached to the package, like we said, 32 gigabytes of HBM. Very different numbers than we're used to in the x86 world, but we can divide this up per core in the CPU. We can use the number of cores we need to balance the memory, but very quickly, it's pretty easy to tune for that memory, as we saw from the research studies, where there's no incentive to tune for it, and they're getting to 32 gig of memory. And very efficient, very power efficient package. Other thing I'll mention here is that there's a tremendous legacy in history of vector supercomputing, and both at Cray and HPE and at Fujitsu, they go back generations in the supercomputing business, and that really comes to bear here. But it's not just in the product and the hardware, because both companies contributed and partnered with ARM for the development of the scalable vector extensions that Brent was mentioning. So it comes together here. The thing about the high bandwidth memory is it's not just a faster pipe, but it's also a three-dimensional delivery. So we get to stack the DRAM. We get to borrow an analogy from a colleague of mine. If you arrange a bunch of books on your desk and you want rapid access to them, you don't spread them out over the whole room flat. You stack them, and then you can just reach and grab them out. In this case, it flows down, but it's essentially the same scenario. A lot of data is very close and very quickly accessed, and that's how we get to a terabyte a second to the CPU.
So let me grab this one. This talks about the ARM architecture, which the Fujitsu system is based on. There's an architecture license involved here. Fujitsu did the entire implementation of the A64FX themselves, and at the front end of that is the ARM ISA. What that does is it enables them to take advantage of the whole ARM ecosystem from a software point of view. And the way that's enabled is through our System Ready program. And the vision here is that software just works on all the ARM devices. So by conforming to System Ready and using the ARM ISA, Fujitsu gets to take advantage of 10 plus Linux distros that you can get support for and just boot up and run on the system. Satoshi jokes that he can boot Windows on the Fugaku system. I don't know that he's actually tried it, but it would be fun to see him do that. And there's a lot of words on this slide to talk about the subcomponents of System Ready. But if you just take away the message that there's a standard here called System Ready, and when a silicon partner conforms to that standard, then on the other side of that is a whole growth of software that's just growing exponentially that they can run with confidence that will operate properly on their architecture. You can switch to the next slide.
Yeah,
then.
and actually, well, let me jump in there a minute, Brent, because I think that's part of the reason that we're seeing so many reports from users consistently to say, man, my software just runs. It just out of the box, I get pretty decent performance, and I focus not on hoarding it, but I focus on finding the parts of it that are going to get me the most performance with this new architecture, and really tuning with it. And because we're using your standards, not only do you get the versatility in the OSs, but you can construct your code so that it's very versatile for future generations of processors using the technology. A lot of effort was put in here to try to standardize as much as we could so that your investments in software engineering are protected.
Right, and it turns out if you have your source code, generally you can type make and your binary will run. And due to the runs on ARM aspect of this, you can take that binary and move it to a different system and it will still run. I want to dive down a little bit on SVE here. We've mentioned HBM a couple of times. SVE is the other side of that. That's the big vector units that are 2x512 in the Apollo 80 case. All of the features that you would expect in a very mature design are present here. The gather scatter, the predication, the floating point formats, all of that. One that I want to draw your attention to here in the middle at the bottom is the vector length agnostic software. So the design for SVE is such that you don't have to specify in your binary what length of vectors you're expecting. It's completely independent. Of course, there has to be an implementation. At the bottom of the stack, there's a piece of hardware which in the case of ARM's V1 architecture is a 2x256, but in the case of the Apollo 80, it is a 2x512 implementation. That same binary runs on both of those architectures because the software does not encode the vector length in it. That helps a lot of ISVs ship just a single binary for the different ARM platforms that they're interested in. And then I'll close with pointing out something that you mentioned earlier, that this SVE feature, vectors done right, is the way I think of it, is really a co-design with Fujitsu and with Cray and with ARM. It was many years in the making. There were a lot of very smart people involved in it and a lot of vector experience brought to this mature technology. It's starting to show up now. Early access, obviously, with this Apollo 80 and HBM, those are the two big features that you can get at now and learn what the future looks like as we go through it. But it's available in ARM standard IP portfolio. You'll see other vendors coming out with this SVE implementation, different lengths, different hardware, that sort of thing.
Yes, and you mentioned early access. This product is robust and has been out in the market with people using it for over a year. So it's not, the product's not new, but this is the first place that you can get access to these technologies. So whether both from the ARM component, as well as it's the first system built with HBM direct attached to a CPU. It's the only one in the world with a HBM attached to a particular high performance computing CPU.
Yep.
It's a whole new level of flexibility that we have not seen in the industry, to not have to require the refactoring for accelerators and so forth. And then it's supported also on the HPE side and the Fujitsu side as well. There's compiler development effort, there's libraries, but there's also things that make this easier as well. When you work with a HPE Cray programming environment that has multiple platforms in mind, but also the high performance computing cluster manager offered by HPE means that it's very easy to deploy these in a mixed environment. So you don't have to make them a standalone island from an administration standpoint. And that's part of what HPE really wants to do is to give you the ability to include this capability, not have to set it up aside. And so even if you're doing a proof of concept level deployment, you still may want to have the administration capabilities there.
Yeah. So one of the fun things that I've learned being at ARM here for a few years is people ask, what is this box like? How is it different from x86? And the answer is you can't tell. It slides into a rack, it plugs into things, it boots up Red Hat, looks, tastes, and smells the same way. We've got this Catalyst program that HPE is leading in the UK. And some of the fun outcomes of that are they've taken some of that hardware, put it in production alongside x86, and the end users couldn't tell. It just looks, tastes, feels, runs like a standard cluster. So that's a really good testament towards the architecture. And then, another thing to put on that, John Masters will say, nobody cares what the silicon is beneath your system. The applications people don't care, but the people who pay the bills care. They care about efficiency. They care about performance and density and cooling and all that sort of stuff. And we'll point out that this same chip powers the world's fastest computer, and it was rated #1 on the Green 500 a year and a half ago. So there's really step functions in terms of performance, in terms of energy efficiency, and it looks, tastes, and smells the same as what you're used to.
Yeah, which is kind of refreshing to be able to see and say that. And that's just you can't make a too fine a point on it. The whole point here is for you to be able to get the work you're trying to do done, not to be a computer scientist for the sake of chasing performance because that's interesting. Got it. So we want you to be successful with your workloads. This is intended very much to be an enabling technology. I don't think as a oil and gas company, as an energy company, that your core business is software engineering, but that's a huge capability, and where you can do that to drive competitive advantage, where you can do that to reduce costs, increase efficiency. Those demands are very serious, and they're throughout the company, and there are a lot of different organizations. And centralizing that isn't always the best answer, although that may be exactly what you do to find out how to make best use of this. And every organization is going to be a little different from that standpoint. But the needs for HPC, they're entirely uncompromising. It's the model fidelity and accuracy needs never decrease. You're never satisfied. That's a reason that years ago we moved to 64-bit computing. The reason that we've probably should have always stayed very aggressively on the path with vectorization and architectural efficiency. But then you've got investments in verification and validation, whether they're formal or informal. You know those models, you know where they do their best, and when things look right and when they don't. And sometimes that's quantifiable, and sometimes that's more of a qualified, expert opinion. But you have to be able to see that. When you bring this capability together with the memory that's so fast and it's close, it provides an opportunity to bring a lot of compute capability that is versatile and doesn't just benefit one narrow part of the solver, but now your interpretation modes might be part of your workflow that you can now readily exploit performance on and keep it close, because you're not going to go refactor those also. So a lot of workflows break when you have to refactor a central component, but it's only one piece of the workflow. So we're seeing people explore in-transit processing and situ processing rather than writing their whole files out to disk, sending it somewhere else, reading it in later for post-processing in a disruptive fashion. And we're also seeing a fusion of data, obviously coming in from observed data, measured data, whether that's operational technologies that are connected now, or whether that's experimental, or whether that's going out and taking field measurements, bringing all that together as an input together with a universe of accumulated simulation data that used to just kind of go through sequentially. Now we can harness that and bring AI to bear, and the system's flexible enough to do that really nicely. But AI is a different problem, and when we talk about performance, this is true 64-bit computing. So as for example, we're going to start seeing exascale announcements on the high performance computing side, and we're seeing some discussion about what I'll call pseudo exascale performance from AI. And I want to call it out because the language is common, but it's very different. And Brent, you're seeing it too, right?
Sure, absolutely. Yeah, if you cut your data needs in half, then you effectively can double your performance by using 32-bit or even lower precision.
Or even lower, like 16 and even seeing 8. So we want to be cognizant of that. And this system and the Fujitsu chip and the ARM engineering and the software infrastructure behind it is a manifestation of that commitment to the kind of true high performance computing that you're used to talking about, and that accuracy and the fidelity and driving all of that. But it's also very much complementary, flexible enough to coexist and bring those other tools in. Machine learning and AI are going to have a whole lot to say about how much we can extract in terms of value from all of this work. And so not discounting that at all. This is a very powerful, flexible system. So with that, I'd like to give the floor over to our colleagues at Fujitsu. Hoshiya-san is kind enough to spend some time with us and talk about some of the work that he and colleagues at HPE and ARM in particular have been doing on some representative oil and gas simulations, giving an idea of some of the performances being exposed to the A64FX.
Excellent.